Thanks for the nice introduction. Indeed, today I'm going to talk about natural language processing, but in particular with a focus on the generation side. I believe that the Katharina, who is now at University of Colorado Boulder, who used to be my postdoc in NYU, already covers the transfer learning and then how to build a very nice classifier that can solve a lot of problems. And today in particular, I'm going to go through a very basics a lot in order to ensure that everyone who participates in this summer school at the end of the summer school knows when they build any of these natural language generation or understanding systems, they know why all those small design choices that had to be made had to be made in that particular ways. So we're going to start by recapping supervised machine learning. I know that you probably have been hearing about supervised learning over and over, perhaps a bit too much so throughout the whole summer school. I looked at the schedule, I'm pretty sure everyone talked about it, but there's a reason why everyone talks about it, because it is very, very important. And then in particular, we often realize that there are a lot of techniques that does not look like a supervised learning, such as unsupervised learning, self-supervised learning, or even reinforcement learning. They all boil down to how to train a supervised classifier. Because at the end of the day, what we do is to reduce all those complicated problems into a sequence of supervised learning problems that we know how to solve. And that's going to be the same for natural language processing and generation. So in supervised learning, we are given a set of data sets. In fact, we are given 3 data sets. One is a training set, we have validation set, and test set. We are often given, let's say, one big chunk, but we have to somehow divide them, partition them into 3 sets. And then we're given a loss function that allows us to compute for each example how good our model's prediction is. We have a set of hypothesis sets that I'm going to talk about briefly in a minute. And then we need to, is either we're given or we have a choice of the optimization algorithm. And then once we have that, the goal of supervised learning is to find an appropriate algorithm or the model that's going to minimize the sum of all these loss functions. And then what we're going to do is we're going to find one point in this hypothesis space that's going to minimize this. Of course, the goal is not really to simply find the one that's going to minimize the loss function over the training set, but to find the model that's going to work well on unseen examples. So we're going to use the validation set. That's the second partition that we talked about. And then once we have selected the appropriate hypothesis space, and then within the hypothesis set, the model that's going to work really, really well on the validation set, then we're going to report or assure ourselves that it's going to work really well on an unseen examples by looking at how well the selected model works on test set. So very, very straightforward framework, but it turned out that this is the foundation upon which we build the entire machine learning ecosystem that includes natural language processing. So then what we end up with is this algorithm. So in a sense, what supervised learning does is for us to be able to build an algorithm without having to design the algorithm ourselves. So when we try to use supervised learning in practice, as well as in research, we need to think about at least 3 points. And then we're going to go through them one at a time quickly before we delve into the actual language modeling or the natural language processing. So the first one is, how do we decide or design this so-called hypothesis set? If you remember from the previous slides, I talked about how we are given number of hypotheses. So it's not going to be just one. And then we need to decide which hypothesis that we're going to use using the validation set. So, but then there's a question, right? What is this hypothesis set? What are these hypotheses that I'm talking about? You must have already heard from one of the many amazing lectures that have been organized at the summer school. However, let's just go through it very quickly. In particular, in this deep learning, and then you have the deep learning, because I talk about deep learning because my lecture is largely about how to use deep learning for natural language processing. You can imagine a hypothesis set as a family of neural network or any kind of neural network design or the architecture that you define. For instance, one of the very popular, the one that actually popularized deep learning in 2012 was AlexNet, which is shown on the slide on the left-hand side. Now, once we decide to use this architecture from AlexNet, then that actually defines a hypothesis set or the hypothesis space. It depends on how you call it. Or of course, you might decide that, oh, AlexNet is too simple. So then I'm going to go for, perhaps unreasonably complicated architecture of the GoogleNet, which is shown on the right side of this slide. And then that one is going to also define a new hypothesis set. And then within this hypothesis set, each element there corresponds to the one particular parameter configuration. So that's why this set is in fact infinitely large. So it's probably more appropriate to call it a hypothesis space, but you get the idea here, right? Yes. And then the goal here is to find one good point in this hypothesis space or the infinitely large hypothesis set using some kind of optimization procedure. So at the end of the day, supervised learning all boils down to finding a particular good parameter point in this large hypothesis set, which was defined based on the network architecture we use. But then we need to think about, okay, what is this network architecture? We need to think about it from a slightly abstract point of view, because at the end of it turned out that we can build however we want the neural net that we want. And then it's going to all work as long as it can be described as an arbitrary directed acyclic graph. So we're going to start with the nodes that are variables or the inputs. So those are the variables that we don't really touch, but are going to be given. And then we just build a graph, and that this graph should not have a cycle. And then this graph is a directed graph in a sense that for every node, there is an edge going out of the node into another node. And then what happens is that once we have this directed acyclic graph, then it fully characterizes what kind of neural network that we're going to build. Because it has the nodes that corresponds to the input, it has nodes that corresponds to parameters of this network, and then it has nodes that corresponds to what kind of computation is being done. So you can think of those computation as doing the convolution, applying some kind of activation function and so on. And then those nodes can be stacked on top of each other as long as there's no cycle. And then what we get out of this neural net is the output we get from the final set of the computational nodes. So what that means is that in fact, these neural nets that we built for solving supervised learning, unsupervised learning, and all the problems in natural language processing and generation, in fact, is not so different from a very simple logistic regression classifier, linear classifier, or even simpler, any kind of one-dimensional polynomial function, because all these computations can be described in terms of a directed acyclic graph. We're going to have an input node. Here, in the case of the logistic regression, we're going to have X, that's going to be the input node, and then we're going to have the parameter nodes, which are W and B. And then we have just a sequence of the computation nodes that are going to first do the dot product, and then next does a summation, and then finally it applies a sigmoid function on top of them. So in other words, when we think about the network architecture, when we think about the hypothesis set that corresponds to the network architecture, and then how we describe them is by building a directed acyclic graph. So far, so good. And then given this directed acyclic graph, now the computation or the forward computation, that is how we use a trained network, can be again abstracted out. So we don't really have to care too much about the individual node as long as we have implemented them once, or better yet, if others have already implemented them. And then this computation, or how we use this trained neural network, corresponds now to the topological sweep, that is the breadth first search. So we're going to start from the very beginning nodes and then apply the computation one layer at a time, right? So in the case of logistic regression, initially we have 3 nodes. The first node corresponds to the input X, and the other 2 nodes corresponds to the weight and bias. And then we're going to do the topological sweep of this computational graph by going through the dot product, summation of the bias to the output of the dot product, and then applying the sigmoid function. So it actually gives us a very nice way to build a generic framework on top of which we can define any kind of complicated neural nets. So yes, so directed acyclic graph and hypothesis that, and because of that, this naturally supports high-level abstraction, and then it also fits with the various, let's say, programming paradigms such as the functional paradigms as well as objective-oriented paradigms. And then it actually allows us to maximally reuse code. And then this is evident from the success of the PyTorch, TensorFlow, Dynet. Well, now I need to add JAX there as well, and Flex, which means that this is a really nice level of the abstraction that we're going to operate on. What it means is that throughout this remainder of my lectures today, I'm not going to go that much detail into individual nodes, except for the attention and the recurrent net at some point later today, because we can now work on top at the level of this level of abstraction. And then we can now focus more on what are the learning algorithms, and then what is the right way to build this directed acyclic graph in order to solve the problem as well as we could. So that was the hypothesis. The second thing is a loss function. Now, what is the right loss function to use? You may have seen a lot of loss functions so far throughout this summer school, but in particular, in this lecture, and then generally in the natural language processing these days, we focus on the distribution or the probability-based loss function. So how we view this supervised learning is that the supervised learner or the neural network is going to compute the conditional distribution over possible outcomes given the input X. So in other words, what our neural net computes is not what the answer is, but given a possible answer and the input, what is the chance that this possible answer is indeed the answer? So for instance, in the case of classification, let's consider binary classification where the input should belong to either positive or negative class, then what our neural net is going to output is a Bernoulli distribution. So it really doesn't give us any particular answer, but it's going to give us a distribution over two possibilities. In the case of multi-class classification, such as in the ImageNet classification, our neural net is going to compute the categorical distribution. So it's going to give us let's say 1,000 probability values that corresponds to the chances of the input belonging to one of those 1,000 classes. Now, in the case of linear regression, our network is not going to again give us the answer, but it's going to give us a distribution that is often centered around the answer that our model believes in it, but with some uncertainty described in the way of the variance. And then we can think about a lot of different things, but the point is that we want our model to give us a distribution over possible answers. And this is often not that necessary if your goal is to build a simple classifier given a very small number of classes, because at the end of the day, you're going to look at the categorical distribution that is given by your neural net and then pick the one with the highest probability. However, in the case of the natural language generation, where our output space itself is combinatorial, that is that the size of the space is exponential with respect to the length of the sequence, the actual probabilities start to matter. So one particular distribution that is perhaps most widely used in natural language processing or the generation is categorical distribution. That is, given X, what is the, well, X doesn't have to be given. That is, given a set of fixed number of classes to which the input belongs, now what is the distribution over them? And then what it means is that my neural network needs to give me, let's say, 1,000 many numbers, assuming that there are 1,000 classes, so that the sum of all those probabilities or the values are going to sum to 1 and are non-negative. So then, it turned out that it's quite simple to implement it using a neural network. So as we said before, any neural net is an arbitrary directed acyclic graph. We will build such a graph that takes as the input X and some parameters. And this graph is going to compute, whatever it wants to compute internally, and then gives us a real values vector that consists of the numbers, as many numbers there are distinct classes in this problem. In the case of ImageNet classification, that's going to be 1000. And what we need is that we need to have just a one node or a subgraph attached at the end of this arbitrary subgraph that we have built that's going to turn these 1000 numbers into 1000 probabilities of a categorical distribution. And to do so, we often rely on the function called softmax. What this softmax does is to first exponentiate every single number so that they're going to become non-negative. Well, they're going to be strictly positive, and then it divides each and every entry by the sum of all the entry, the exponentiated entry. So you end up with the numbers that are strictly positive, and they all sum to 1. So softmax is going to be like the deactivation function we are going to use in natural language generation in order to describe the distribution outputted by this neural network. And then we'll talk about why this is the distribution we use. And then once we decide or believe that it is a sensible way to have a neural net always output a conditional distribution over all possible choices that is a y given x, then the very natural way to define a loss function automatically arises, and that is to use a negative log probability of the correct answer given the input. The idea is that we are given a training set, and then this training set consists of the training instances, and then each instance is a pair of input and correct output. Then our goal is for our neural network to assign as high a probability as possible to the correct answer according to the training set. And then because our neural net outputs a conditional probability, that's naturally defined as the trying to maximize the log probability of the correct answer. So why are we using log probability instead of just probability? There are many reasons, including the numerical precision issues, but that's definitely out of this lecture scope. But trust me that you want to use this one. And then if you want to put it into a term of the loss function that we want to minimize instead of maximize, then it's simply the negative log probability of the correct answer given the input. And then that's the loss function that we are going to use throughout the entire lecture today. So, okay, we know how to define a hypothesis set, and then we're going to talk about what are the good hypothesis set for the natural language processing shortly. And then we now know what kind of loss function we're going to use. It's going to be just a negative log probability. And then now, of course, we need to think about, okay, what is the right way to optimize this loss function with respect to all the points in the hypothesis set in order to find a good solution. And of course, you must have heard it over and over, probably tired of it. The idea is to define a loss function to be differentiable and often decompose over examples, although that's not necessary that much. And then we're going to rely on the availability of the gradient of this loss function with respect to all the parameters. And then once we have this gradient, then we can use any of the off-the-shelf, I'm sorry. Right, so the order is a bit wrong, but once we have the access to this gradient, however we compute it, then we can use any of the off-the-shelf gradient-based optimizer, including gradient descent, LBFGS, conjugate gradient, or whatnot. However, due to the scale of the data at which we operate, we often resort to stochastic gradient descent, where we control the amount of computation that is done at each update by selecting only a small subset of the training data at each time. And then that has to be done randomly. And then this actually allows us to make as many updates as we want without having to wait for each update to go through the entire data set, unlike many of the off-the-shelf algorithms that require us to do so. Now then, this actually brings us the question of how do we actually compute the gradient of this loss function? We used to do the manual derivation quite a lot, like 15 years ago, but we don't do that anymore because of the advances that we have made in terms of automatic differentiation. And then automatic differentiation has a really fascinating theory and the practice behind it. But if I have to make the most simplifying, let's say, description here, then the idea is to use the chain rule of derivatives as well as possible. Because we have built a directed acyclic graph, And then with all those nodes and variables that make the entire thing differentiable, we can now implement the Jacobian vector product of each node and then simply train them following how the graph was built. I'm pretty sure you already heard about it, but this turned out to be an extremely powerful idea, because what that means is that as long as we build a directed acyclic graph that's going to form our hypothesis set, following or the satisfying some of those constraints, such as the differentiability or the differentiable almost anywhere, everywhere, then we can now automate the whole process of the forward computation as we saw before, as well as how to compute the gradient of the loss function with respect to all the parameter nodes, and then if necessary, even the input nodes as well. And then this can be done all automatically without us, the practitioners, know about the underlying details to the T. So that's great. And then once we do that, we just feed it into the off-the-shelf gradient-based optimizers. I say off-the-shelf, and then people say, oh, but look at this, look at the stochastic gradient this, and I gotta choose this and that and that. But at the end of the day, if you think about it, what do you actually use? You do the from torch import optim or optimizer optim, and then you have the optim.atom, and then you put the model parameters, and then give a couple of the hyperparameters, and even the optimization itself is going to be done automatically for you. Now, just one thing I want to quickly touch upon, because it does become very important, especially in natural language processing, is the always stopping. Because there are many different ways to solve the same problem, we need to have a very good test set or the validation set that is constructed for us to be able to see whether the classifier or any kind of machine learning model that we are building for solving this problem capture the appropriate aspects of the data. We need to build a validation set and do the always stopping very, very carefully. And then the idea of always stopping is very straightforward in the sense that we have a gigantic hypothesis set, and we're solving the problem of finding one point in this infinitely large hypothesis space by using gradient-based optimization algorithm. And then what you can imagine, or what you can imagine in your head, is that we start from somewhere, theta 0, and then we're going to make a trajectory within this hypothesis set. And then in this trajectory, we are generally making progress toward finding a point with the minimum loss on the training set. But of course, on the way, we're going to pass by the point at which the validation loss was minimum. So then what we want is that we want to backtrack and then use a solution that does not have the minimum training loss, but the minimum validation loss within this trajectory. And then this actually does make a big difference. And in particular, one thing that it's important to realize, especially in natural language processing and generation, is that the loss function that you use for training does not have to be the loss function that you use for validation or the always stop. Because we are going to talk a lot about the generation. In generation, the quality of the generation is really, really difficult to capture. And there are many different proxy metrics that people have come up with, but those proxy metrics do not often allow us to directly minimize or to maximize them. So what happens is that we need to come up with yet another proxy, which is the negative log probability that we know often is differentiable with respect to parameters of this directed acyclic graph or the neural net that we're going to build. And then along this trajectory, we're going to check every once in a while how well this parameter along this trajectory works using the original proxy metric that we had, such as a blue score and whatnot that we're going to talk about briefly later on. And then this is a very powerful scheme, because what we see often in this natural language generation in particular, because that's the one that I'm familiar with, is that the loss function that we use to train a model and the loss function that we use in order to tell how good this system is generating or solving this task itself starts deviating as we train further and further. Sometimes training loss stops improving. However, if we simply continue with the stochastic gradient descent, the task loss might go down further. of course, the other way around happens as well. So all this typing is very, very important. So let's keep this in our mind for now. So we talked about these three things that we need to discuss. Number two, the how do we decide a loss function? We decided, okay, we're going to simply use the negative log probability. Number three, how do we optimize the loss function? We decided to simply use a gradient-based optimization. Now, it turned out that the number one is not that easy. We are working at the level of the abstraction of the directed acyclic graph, but it turned out that how to build that graph has to depend heavily upon the problem that we are solving. So essentially the remainder of this lecture and then for the next, let's say, 2 hours are going to be all about how to design a hypothesis set or how to design a neural network in order to solve the problem in natural language as well as we do. So we now move on to language modeling as supervised learning. And then language modeling is the first thing we're going to learn. However, we'll have to talk a bit about the text classification first, which I believe you already have learned by Katharina Kahn. And then there is, in particular, she focused on the transfer learning. But here we're going to like take a many step back and then look at the very basics of not about the data, not about the problem itself, but what do we mean by the text classification and what is the usual practice in doing so. That said, Rodrigo, is there any questions on YouTube or in Slido? Because I don't have access to them, so I can't really tell myself.
No, so far no questions.
All right, no questions. Okay, so we'll continue with the language modeling is supervised learning. And then to do that, we need to talk about the text classification. Text classification is a very traditional problem. And then just like any other classification problem, we have input and output. And then output is going to be a category to which the input text belongs. And then there are often a fixed number of categories, although this is not necessary in particular with natural language because each of the categories could be described by a language, which allows you to work with the set of categories that varies from one example to another, one task to another. But that's a bit out of the scope of this lecture. If you want to know more, just ask me later. And then now, what's particular about text classification is that the input is going to be a natural language sentence or paragraph. So some of the examples include sentiment analysis, which is not really the problem in my opinion. However, everyone takes this as an example. So that is that is this review on Amazon positive or negative? Some kind of text categorization is, of course, another example. So somebody wrote a blog post. Can we actually tell automatically to which category it belongs? And then there's intent classification, often used in the building a goal-oriented dialogue system. Is this question from a user about a Chinese restaurant? So there are many different examples of the text classification, but at the end of the day, we are going to work at the level of the abstraction where we say that the input is a natural language sentence or paragraph, and the output is going to be a set of fixed number of categories. So then we need to think about how to represent a sentence. Interesting thing about text is that it's a variable length sequence. So the size of the input is never fixed. Size of the input can vary from one sentence to another, one paragraph to another, one document to another. So we need to think about how to represent them at multiple stages. But in the very first stage, we need to think about what is the right way to turn this text into a form that allows us to manipulate mathematically. So one of the most let's say the usual way to do so is to consider it as a sequence of tokens where each token could be anyone from a fixed vocabulary, and the vocabulary has a fixed size. And then there are many different ways to do so. I gave you an example here that is written in Korean, so my guess is that almost none of you could read it, but you can see that those three bullet points are different ways to represent the same sentence. The first one is going to be, we're going to simply say that it's a sequence of the blank space separated tokens. Second line says that is going to be a sequence of unique and segmented tokens that goes beyond the separation by the blank spaces. And then the third one says that it's simply going to be a sequence of syllables, including the blank spaces as well. But you can imagine making a lot of different, you can imagine many different ways to define what it means to represent a sentence as a sequence of tokens, right? But today we're not going to go into the details of this because this has to be very much language specific, and then we really can't really spend too much time on them. But whenever you build a system for a particular language, you need to start from thinking about how to represent a sentence. Now, once you decide a way in which to represent a sentence, you then end up having every sentence or the document as a sequence of integer indices. So what do I mean by integer indices is that each and every token is going to be turned into an index that allows you to recover the original token. So the vocabulary that we talked about is not really a set in when we try to implement anything, but it's more like a table with the index column and then corresponding token column. And once we do so, very nice thing happens is that we now can focus on building a natural language system, a language processing system, or the text classification system without having to worry about the actual language that we are dealing with. So we are trying to abstract away the details of the particular language we're building this system for, but we're going to focus on the algorithm that can be applied to any language as long as you can represent the text in any language into a sequence of integer indices. So then we need to now think about, so now we have a sequence of integers, but we're not going to use the integers directly. Why not? Because those integers don't really encode any meaning to start with. So the fact that one of the words has been encoded as 1000 does not mean that this word is any more similar to another word that was encoded into 1001 than yet another word that was encoded into 1 million. So we need to somehow move away from this integer, because we chose integer because that's a quite natural way to implement this hash table, but we don't have to use it. So what we want is that we want to turn it into yet another representation. So this is stage 2 that assumes nothing. That is, we want to use a representation of each token that does not encode any similarity among themselves. And that's why we often use so-called one-handed encoding. In one-handed encoding, we have a vector for each word, and then it's all 0 except for one particular item whose index corresponds to the integer index of that word. So it's going to be 0, 0, 0, 0, 0, 1, and all zeros. And then this allows us to encode the entire vocabulary quite, well, not efficiently, but effectively. And then what's interesting about this one-handed encoding is that you pick any pair of vocabulary, look at their one-handed encoding, and then the distance between these two is exactly the same, unless you chose the same one. So when you chose a pair of two distinct words, their distance to each other, according to this one-handed encoding, is identical for any pair you take. So this is indeed the encoding that assumes nothing. But then now, that doesn't help. So what are we going to do? This is a representation that doesn't really assume any meaning. So what we use is the table lookup, as you already have learned from the Katharina earlier. And then in this table lookup, what we have is a Wayne matrix, very large Wayne matrix, which contains as many vectors as there are tokens in this vocabulary. And then this can be implemented as a simple matrix multiplication by having a Wayne matrix that is multiplied from the right or the left, depending on how you decided to implement it, the one-hot vector of the corresponding word. Now, it turned out that multiplying a large matrix with a one-hot vector is identical to simply indexing out a row or column. And that gives you a vector, continuous vector, that encodes the meaning of this word, particular or in the context of this text classification problem you solve. Now, you must have heard about all those word2vec and so on, but these meaning vectors or the word vectors are automatically estimated to solve the problem of text classification. So we're not going to assume that we're going to use a pre-trained embedding or anything like this. So we're going to say that, okay, this is just a part of this directed acyclic graph, and that this is a part of this DAG as a parameter node. So now then we need to think about how to represent the sentence. So we now know how to represent a text, and then in particular how to represent each token. Now we have a sequence of these vectors, right? So I'm going to use a E1 to ET there. So we have an X that is a sequence of continuous high dimensional vectors. Now, how are we going to represent a sentence? Because as we talked about it earlier, eventually we need to end up with a real valued vector whose dimensionality matches the number of categories. And the issue is that we have a variable length sequence of continuous high dimensional vectors, and that we need to compress into a fixed dimensional vector. So we need to think about what we should do. And then the first thing we can think of is so-called continuous backup work. That is, do we really need to take into account the order of the words? This sounds pretty crazy, because we're going to ignore the order of words and then say that, the input text is not really a sequence of high dimensional continuous vectors, but simply a set of those vectors. And then once we have a set of those vectors, or the set of the token vectors, the best we can do, there is a weird theory behind it with the deep sets and so on, is that the best we can do is to average them, because there is no order. There's no such thing as this token comes first, that token comes first. No, nothing like that. So then we're going to simply average this high dimensional vector to obtain so-called continuous back of words. It's a back of words because once you put items in the back, then you forget about the order in which those items went in, right? And then, of course, you can think about generalizing into back of engrams. So you're going to build a vocabulary that consists of the engrams, where the engram corresponds to a chunk of text that consists of the n consecutive words. And then it turned out this is extremely effective in text classification. And you can actually kind of imagine why this is so. Let's say you go on Amazon and then you want to buy something. The first thing often what we all do is to go to the reviews and then read how people who bought this product felt about it. And then does anybody actually read the review really, really carefully? I don't think so. Often we look for a salient words there, such as the not, horrible, amazing, excellent. So in some sense, we rarely read the entire review, but trying to see what were the important words that we thought are associated with telling whether the person liked this product or not. And then that's probably the reason why this back of words or the back of engram works so amazingly well. And in practice, you Google fast text, which is the library coming out of the Facebook AI research, and then just download fast text. And then it's going to do the amazing optimization for you, whatever the text you throw it. So we have learned one way to represent a sentence in this neural network. So let's just look at how the DAG looks like. We have the input, and then for each token, it's going to go through the table lookup in order to form a high dimensional continuous vector. And then these vectors are going to be averaged. And then once you have the average vector that is a continuous back of word, we can again put another arbitrary directed acyclic graph on top of that has its own parameters theta. And that eventually goes into the output of the graph, eventually goes into a softmax layer. And then that is our continuous back of word text classifier. And of course, once you build this, then you can train this network end to end without you having to implement anything yourself. We're going to rely on the automatic backpropagation, and we're going to rely on a well implemented stochastic gradient descent to train this classifier. Now, one thing that you notice about this back of words or the back of engram is that first of all, okay, it ignores the order. That's one thing. But then in back of engrams, we recovered a bit of order information, but that's too local. We're only looking at a local relationships. And then all those small local relationships are globally put together to form the representation of the entire sentence. So perhaps then we should go beyond it. So what would be the most obvious way to go beyond that is so-called skip engram or the skip bigram. And then that's connected to the concept of the relation networks from 2017 that came out of DeepMind, is that instead of looking at the nearby words as a single unit, but we're going to look at all possible pairs of tokens. So we have a sentence, we're going to look at all possible pairs of the words, and then trying to see what kind of those skip bigrams exist, and then based on that, trying to make a decision. And again, all we need to do is write a directed acyclic graph, and then for a particular one skip bigram that consists of xi and xj in this sentence, we're going to feed each one of them into the table lookup layer in order to turn them into the continuous vectors. Then we're going to somehow turn them, we're going to apply some kind of linear transformation, simply sum them, and then feed it into some nonlinear function, after which we again apply the linear transformation. And what we do is we're going to apply this relation network or the relation module over and over for every possible combinations of the tokens. And of course, you can think about generalizing this to triplets and so on and so on, but of course, at the expense of computational efficiency. So if you look at the directed acyclic graph, because that's the only thing that we actually need, right, in order to build this kind of neural network, then what we end up with is that we have two sequences which are just copies of each other, and then we're going to look at every possible pair, and then for each pair we have this relational network module that's going to give us some vector representation, and then all these vector representations are now averaged as we did with the continuous backward in order to form a single fixed dimensional vector representation of the input sentence. So, okay, seems like the skip bigram is a slightly better or the perhaps more flexible representation than. Okay, I'm sorry, I somehow pressed something wrong. But it is still a bit, what can I say, less satisfactory in the sense that we are going to look at all those pairs, but eventually we're going to average all those representations. So instead, can we actually keep this information throughout the entire sequence rather than just doing the average too prematurely? And then that's where the idea of the convolutional network comes in. So instead of trying to look at the engrams at a very shallow surface level alone, and then compute the average, we try to capture these k-grams or the n-gram, but I'll just use k because n is a bit overloaded, k-grams hierarchically. So unlike in images or in videos where the 2D or the 3D convolution are much more common, in text, because we're talking about the sequence, we work with the one-dimensional convolution. And then we're going to stack these convolutional layers on top of each other in order to capture a larger and larger n-grams without having to increase the number of parameters too dramatically. Because in usual backup n-grams, as the n grows, the number of the unique n-grams that we need to consider grows exponentially with respect to n. However, in the case of the convolutional network, the use of these continuous representations allow us to avoid this exponential growth. And then it also fits very well with our intuition of how sentence or a text should be understood. That is, we start from the sequence of tokens, and then we're going to capture those multi-word expressions such as New York. And then we are going to combine them to understand those phrases. And then those phrases all combine with each other in order to form a sentence that we're trying to extract the meaning of. So of course, we are not going to follow these strict definitions of the tokens, multi-word expressions, phrases, and sentences. However, this convolutional network can capture such relationship implicitly when stacked on top of each other. So, and then in practice, it's yet another operation or the computational node in directed acyclic graph, meaning that there are already extremely efficient implementations available in all the major frameworks that you can think of. And then people have been studying this quite a lot to come up with the efficient and effective ways for text convolution in text classification, such as a multi-width convolutional layers, dilated convolutional layers, and gated convolutional layers. So the convolution was nice, but I don't know if you have noticed, but the convolution still cannot capture the context of the entire sentence or the entire document, because the size of the so-called receptive field of each vector after the convolutional layer, multiple convolutional layers, is still fixed. It depends on how many layers you have, whether you use a dilation or not, and what the kernel size was. Can we then somehow generalize this convolutional network so as to avoid fixing the size of the maximum size of the receptive field? And can we do so by combining the idea from the relational network and convolution? And if you think about relation network could actually go look at the entire context by looking at all possible pairs. Convolutional network could be very efficient, could be stacked, and then could keep its representation of the locations by looking at all this, let's say, the local context. Now, can we combine them together? It turned out that it's definitely possible. There are many different ways to do so. We're going to actually look at 2 different ways today. This is one way to get to the attention, in a sense that we can view the convolutional network or the convolution as a weighted relation network. So we're going to look at every pair of every pair of tokens centered at one token within a small window, and then we compute some vectors for every pair, and then we're going to simply average them, but with particular weighting scheme. That is, if you're far away, you're further away than the window side, the weight is going to be 0. If you're within this window, then weight is simply 1. So it's going to be just adding all those feature vectors from the local window 1. And looking at this, you realize that perhaps we can generalize it by making sure relaxing this constraint that the weights can be either 0 or 1. Perhaps we can make the weights to be some continuous value. And then that's how you end up with the attention mechanism that allows you to look at the entire sentence rather than just a local window like in convolution. And in order to get these weights, we can use the idea from the relational net. So whatever goes into this neural net F is going to be weighted by yet another neural net that takes as input the very same input. So it's going to look at this pair and then tells us this pair is very important or not for solving this particular problem. And then that's how you end up using both the convolution and relational network, or the ideas from these two, combine them in order to end up with the self-attention. So for each location in the input, we're going to look at every pair centered on that one. And then there's going to be a weighting function that is implemented as a relational network. And then, well, I mean like this. So both of them are implemented as a relational network. And then this weight is going to be multiplied to the vector that you get out of this pair. And then that one works as and then all those vectors are going to be summed in order to form the new representation. This is not restricted to the local window, while it has an option to ignore irrelevant long-range dependencies, unlike in the original skip diagram where every long-range dependency had to be captured. And then, of course, you can further generalize this to multi-head and multi-hub attention, which I'm going to talk about as a second way to arrive at the self-attention soon. So we have a recurrent neural net, which tries to avoid some of the weaknesses of self-attention, such as quadratic computational complexity, as well as the fact that the self-attention really cannot, in principle, do the counting or many of the very trivial things that we would expect any of our neural network or any kind of computer system that works on a sequence by turning the whole computation into an online computation. Now, when I say online compression or the computation, this is different from the online machine learning that you learned about, I think, yesterday or the day before, where you learned about, recurrent minimization and so on. It's just purely about the forward processing of the input sequence. But for recurrent neural network, we're going to talk about recurrent neural net much more in next hour when I talk about the language model and machine translation. But the idea here would be that instead of going for the self-attention, we have an option to go for the recurrent network that's going to read the entire sequence, either left to right, right to left, or in both directions in order to get us a representation. And this representation, again, is going to be the representation of the entire sequence without ignoring any of the temporal or the ordering information. So we just learned 5 ways to extract sentence representation. All but continuous backward word, we end up with a set of vector representations. And then we can stack all these different approaches in order to get the best out of all these sentence representation extraction methods. And then you can make a trade-off between computational efficiency and statistical efficiency in most cases. And at the end of the day, for the particular case of the text classification, we need to average or max for these vectors or the representations in order to solve the problem. However, in the case of language modeling and machine translation, which we're going to look into in next hour, that's not necessary. So I think that we have 8 minutes of break before the second lecture. Rodrigo, is there any questions that I could answer?
There is indeed one. So is there a standardized way to sequence the tokens across research groups?
So standardized way. So I mean, like there's no standard. These things are changing like every month, every like the half a year or so. However, so what used to be done is that the people used to come up with their own tokenization scheme for their own languages. However, now what people are doing is that even for tokenization as well as segmentation, we try to rely on the more of the automated machine learning algorithms. And then about two main algorithms that people use are the sentence piece algorithm from Google and the bypair encoding from University of Edinburgh. And then those are largely standardized as in they have all open source code that you can use. And then once you run that algorithm on the text that you have, then you end up with a vocabulary of the unique tokens and then how to segment any new sentence. So then as long as you release them together with your system or your paper, then others can easily reproduce them.
Great. Well, then we can have our break. So until 7 minutes, until 6 p.m. Now it's 5:53. So short break. And
you'll be back in 7 minutes, I guess. Yes.
Yes.
All right. Sounds good.
And you can just turn off your camera feed and audio, and then we can meet again in 7 minutes.
Okay. Sounds good.
Hi, Genke.
Okay, shall we continue then?
Yes, let's continue.
All right, so yeah, welcome back. So, somehow I haven't really talked about the actual language that much because text classification turned out to be very much of the standard thing that you have been doing, except that the now input was just text. But now let's talk about the more language stuff now, and then we're going to start with the language modeling. Language modeling is a very interesting problem in a sense that it's an unsupervised learning problem where the input is going to be a sentence, but then the output is nothing that we have any correspondence to. It's just a probability of the input sentence. So the idea is that if we want to be able to tell whether a given sentence is likely or not according to our data. So in other words, in order to do, well, not in other words, in order to do so, we have to build a language model that can capture the distribution over all possible sentences. That sounds like a daunting task because if you think about how many sentences there are, even with the maximum length fixed to some value, it's going to be the size of the vocabulary to the power of the maximum length. So it's a pretty big space. So how are we going to solve this problem? It turned out that one of the most effective way to do so, or even efficient as well, is to turn this problem of unsupervised learning into a sequence of supervised learning. And in doing so, we end up following the paradigm called autoregressive modeling, which I believe you may have already learned about from the various lectures during this summer. And the basic idea here is that the distribution of a sequence is going to be now rewritten as the product of the distribution over each token given all the previous tokens. And then this equality just holds exactly thanks to the definition of conditional distributions, right? And by doing so, we somehow have turned this problem of unsupervised learning into a set or the sequence of supervised learning problems. Because if you look at this particular conditional here, as well as this conditional and all the other conditions, what we end up with is a conditional distribution over possible set of words, right? So you can think of it as a set of fixed number of categories given the part of the sentence. And the part of sentence is just a sentence. What that means is that for language model, it turned out we don't have to really solve this complicated density estimation problem as it is, but we can now reduce this problem into a sequence of text classification problems. And then we're going to tackle this text classification problem instead. And then we combine them into a one system that's going to give us how likely a given sentence is. And the funny thing is we already know how to build a text classifier using a neural network. Let's just look at one particular example here. We had x1, x2, xt minus 1. So we don't have a full sentence, but we now have a prefix of the text. But prefix of a text is really nothing but just a text. So we have a sequence of tokens. Each token is then turned into the high dimensional continuous vector using the table lookup layer. And then a single table lookup layer is applied to every single token. And then we learned 5 different ways to extract the sentence representation. And then we can use any one of them. We can use continuous backward, we can use recurrent neural network, we can use self-attention, we can use convolutional network, we can use relational network or the skip bigram. And then once we have the representation or the vector representation of the entire prefix, then we can have an arbitrary computational graph there. So we can make it as deep as we want, that as long as it ends up giving us a real valued vector whose dimensionality matches the size of the vocabulary, where the vocabulary in our case corresponds to the categories in text classification. And then that real valued vector can be turned into the distribution, categorical distribution, using the softmax function. So then it's really interesting. We already learned without realizing how to build a language model because we learned how to build a text classifier. And given a sentence, now we can use this text classifier to score them. And then the score is given as the log probability of a sentence. And this log probability of a sentence can be rewritten. Oops, I'm actually missing this. Log probability of sentence can be written as the sum of the log probability of the correct output category, that is the word, given all the previous tokens. There is a sequence of prefix sequence, and then it is just a sum over all the tokens. And trying to train this model corresponds to maximizing the log probability of the observed sentences from our training set, which is to trying to train this text classifier to be able to assign as high log probability as possible to the correct following token given all the previous tokens. So it really is text classification, not just anecdotally, but the whole formula tells us that we have to train this text classifier to maximize the log probability of the correct next token given all the previous ones. And then that's how we're going to train this text classifier and thereby getting the language model. Once we have this text classifier, then we can compute all these probabilities because our text classifier returns us the categorical distribution. And we multiply all this and end up with the actual probability assigned by our model according to the data to this given sentence X. So let's think about the idea what this is that it's very natural. So let's say a sentence given is in Korea, more than half of residents speak Korean. I think that's true, but of course I haven't really looked it up carefully, but let's say that's true. Then how are we going to tell how likely this sentence is we're going to first say that how likely is it that the word in appears at the very beginning of the sentence. And then we're going to say how likely is it for us to see Korea following in. That's pretty likely, right? Because in is often followed by a name of the place. Korea is a country, and then it also refers to some place. And then how likely is it to see more following in Korea? Maybe not too high, but still compared to many other options, this is reasonably okay. And then what is the chance that we're going to see then after in Korea more? Very high, right? And then we're going to simply multiply all these likelihoods or the probabilities or sum all the log probabilities. And then that's going to tell us how likely this entire sentence is. Makes sense, right? And this actually allows us to do interesting things. There is a reason why you probably have learned from Katharina that one of the most successful way to transfer knowledge from a huge amount of data for the problem that you want to solve in natural language understanding is to train the whole thing or pre-train the large neural network as a language model, because a lot of problems in natural language, in fact, boils down to telling how likely a given sentence is. So let's think about one particular example of trying to doing some kind of QA. And then the question is, what is the language that is being spoken by more than half of the residents in Korea? Now I can answer this question by simply scoring all possible languages, scoring each of all possible languages by constructing in Korea, more than half of residents speak that particular language. For instance, let's say I had a choice I had two options. One is Korean and the other was Finnish. Then what I'm going to do is I'm going to take this language model that I have trained as a text classifier and then trying to score in Korea, more than half of residents speak Korean against, and then score in Korea, more than half of residents speak Finnish. If the first sentence is deemed more likely, my answer is going to be that Korean is the answer to this question, original question. If the second sentence was deemed more likely, then my answer would have been that it is Finnish that is being spoken by more than half of residents in Korea. So what it means is that the language modeling does not look like any problem that anybody wants to solve. However, it turned out that language modeling does incorporate a lot of problems within itself so that it can be used for various other purposes. So let's back up a bit because of course, we said that, we know how to build a text classifier using neural network, but before neural network, what were people doing? One thing that people have been doing is to assume a Markovian property. One of the reasons why you want to assume the Markovian properties is that if you don't use this kind of continuous representation or the neural network, it's very unclear what is the right way to build a classifier that can handle a variable length prefix. Because this language model, by definition, should be able to cope with any length, sequence of any length. So then, let's say we assume this Markovian property, that is that we are only going to look at the n or fixed number of previous tokens in order to predict what the next token is going to be. Then how we actually estimate these probabilities. In particular, we need to look at each and every one of these probability, and we can now use the idea of the definitions of the conditional margin probabilities in order to turn this conditional probability into a fraction, or the fraction of the probability of looking at the entire thing divided by probability of looking only at this prefix. And we can estimate these conditional probabilities from the data using maximum likelihood estimation. And the maximum likelihood estimation is relatively straightforward notion, is that we're going to toss the coin a lot and then look at how often this coin landed heads. And then that's going to be the probability of this coin landing in heads. Sounds easy. And then it's even easier because we don't even have to toss the coin in our case. Somebody already tossed the coin for us, that is the internet. So everyone in the world has been participating and helping us build an amazing language model by writing something and make things online publicly accessible. So data collection is automatically done, and then all we need to do is to count how often things happen. So in the particular case of the engram probability, instead of the coin that we toss, you can think about, we're going to count the number of occurrences for the actual engram. That's going to be the numerator. And then we're going to count the number of occurrences of all engrams of the form, that is prefix and whatever follows. So that's going to be the numerator. And then simply divide the former with the latter, you get the estimate of this engram probability or the conditional probability. Now, this makes sense, right? This definitely makes sense. However, let's look at one example. We want to check what is the probability of university following New York. Then what we're going to do is we're going to count all occurrences of New York University. So that's going to be the numerator. And then we're going to count all occurrences of New York followed by anywhere. So there's going to be New York State, there's going to be New York City, there's going to be New York Fire, New York Police, New York Bridges, and so on. And then just sum all of them. Then that's going to be the denominator here. And then the probability of university following New York, according to our data, is going to be precisely this quantity that we compute. There are a number of problems, and then two major ones that are not independent but interrelated with each other. One is data sparsity. And then this data sparsity is very, very crucial issue. So let's say I want to compute the probability of a sentence, a lion is chasing a llama. Following the paradigm of the autoregressive modeling, we can compute this as a product of probability of A starting at the very beginning of the sentence, probability of lion following A, probability of is following a lion, and then we're going to assume that it's a Markovian model where each conditional is going to only be conditioned on the two previous words. So it's going to be further multiplied by the probability of chasing following lion is, multiplied with the probability of A following is chasing, and finally multiplied by the probability of llama following chasing up. The first few probabilities or the conditional probabilities all look reasonable. However, what is the chance that we're going to see a engram, so 3 gram, chasing a llama? Very unlikely. In fact, if you look for a Google Ngram viewer and then look for this engram, it's very likely that you're going to see a 0 occurrence, at least until 2015, because I started to use this as my own example in various places. So it might actually show that the Google may have already indexed the entire internet. So it might say that, oh, it's not like 0 probability, but chances that whatever corpus you're going to use, chasing a llama is going to appear is 0. Then, however likely all the other engrams were, the probability assigned to this sentence by our engram language model is going to be 0 because of this one particular engram. So that's the issue of the data sparsity that's connected to lack of generalization. Second issue is the inability to capture long-term dependencies. This is a bit trivial in a sense that because we made an assumption of the nth order Markov property, our language model just simply cannot capture any dependencies that go beyond this engram model. Let's take as an example this weird sentence. Let's say the same stump which had impaled the car of many a guest in the past 30 years and which he refused to have removed. If I wanted to guess what's going to follow he refused to have, it's very difficult to guess that it's going to be removed. However, if I had access to the entire prefix, and if I saw that there was a stump that this person refused to have something to do with, then suddenly the removed makes so much sense. Unfortunately, this engram language model won't be able to capture that one. So let's look at some of the traditional solutions. So first, traditional solution for the traditional solutions for the first problem of data sparsity is to simply smooth the whole distribution. In particular, the simplest, let's say, smoothing technique called the add epsilon or the add alpha smoothing is saying that every engram possible should not have 0 probability. So every engram is going to have some non-zero probability. And how we do that is by adding some epsilon constant to every count that we get. And then by doing so, we are never going to assign 0 probability to any engram. That avoids the issue of having a 0 probability sequence just because of one particular engram that never happened in your data. Of course, you notice that this is not really the greatest way to go because it's going to assign same weird probability to both chasing a llama as well as any other gibberish, while we know ourselves that the chasing a llama is just so much more likely. So if we can be a bit smarter, and then we can go into the idea of the backup. That is, if a particular engram did not appear in our data set, we're going to look at n-1 gram, n-2 gram, until we find a shorter engram that actually appeared in our data. And then eventually we're going to end up with just a single word. And then our hope is that that word actually appears in the data. But we're not going to go into too much of the detail of the smoothing and backup, just too many things to cover today. Unfortunately, there is no viable solution to this long-term dependency issue, because as we increase n, the size of the window, then of course this whole problem of the long-term dependence disappears. But as the number of all possible engrams grows exponentially with respect to n, the data sparsity gets more and more severe. In other words, we cannot really solve these two problems altogether. We can solve the problem of the data sparsity by decreasing n, or using some dumb, let's say, smoothing methods, or we can solve the problem of the long-term dependency by increasing n. However, that makes the first problem so much more severe. So there are some conflicting goals that need to be met here, and then that makes it really difficult to use the traditional engram approach for the actual language model. I mean, not that it's not impossible. People do use it, yes. So let's see. So then let's try to tackle one problem at a time. And then the first problem we're going to tackle is the generalization. So we talked about how the lack of generalization is an issue with the data sparsity. Why is that? You then start thinking about, okay, how did you know that chasing a llama, which is an engram that you've never heard of before, is likely? The reason why we knew that was likely is because we know that llama is a mammal that has 4 legs and they run around, and then they are not really the carnivores, so it's very likely that our carnivores are going to chase them. So that's the reason why we thought it was not too unlikely that we'll see chasing a llama. So then what that means is that if we could somehow encode the similarity or use this information about the similarity or our knowledge about those similarities among all these tokens, then we can get around the whole problem of data sparsity or the lack of generalization. Of course, the unfortunate thing is that extracting the similarity alone is a problem that can benefit heavily from this data-driven approaches. So we are now into this weird case of the cyclic, let's say, argument. If we know the similarities among the words, then we can solve this issue of the data sparsity. But in order to solve this data sparsity, but in order to capture these similarities, we actually have to solve the issue with the data sparsity because we always work with a limited amount of data. So we somehow need to solve them all together. And it turned out that using this continuous representation with a table lookup layer indeed is a solution to that. Already in 2001 and 1999, Yasha Bengio in Montreal and his colleagues came up with the idea that if we simply replace this count-based estimate of the conditional probabilities in this engram model with a neural net text classifier, then the problem of data sparsity disappears and the amazing property of generalization arises or emerges automatically. And then you already know why, because Katharina explained it, and I even saw her slides in advance, and it does look like she explained it very well. But let's just talk about it just once more, because it is an important concept, right? So let's see, these are the things that I just told you about. But the important thing comes here. So let's look at this particular example where we are going to assume that there are 3 examples. There are 3 teams left for qualification. 4 teams have passed the first round and 4 groups are playing in the field. And we want to know what is the probability of seeing groups following 3. So it's the probability of probability of group given 3. Now, one thing you notice is that there is no 3 groups in the training example. So if you simply do the counting, then our language model is going to tell us that the probability has to be 0, or it's not even well defined. So we have to be careful there, right? But then, interesting thing is that if you use this kind of continuous vector space, there is a natural tendency to compress the information because we use a fixed number of parameters, and also we use stochastic gradient descent, which cannot really explore this entire space of the parameters fully. It's going to always stay near where it started. And then that, together with a finite number of parameters, lead to the tendency of compression in this neural network. And then what that means is that this neural net will have to organize its continuous hidden space in a way that the similar items have to lie next to each other. So let's look at what's going to happen. So 3 teams was the first example. So 3 is going to be mapped to some point in this continuous vector space. And then based on that, this neural net is going to say that the teams should get a high probability. Sounds good. And then we're going to have now the next example that's going to be 4 teams. And because of this tendency of compression, what this neural net is going to do is trying to put this 4 as close as possible to 3 in this continuous vector space, because once that's done, then this neural net does not have to change anything about the output. It can simply say that, when 4 is given, teams should also get high probability. And then the third example is 4 groups. Then again, the neural net already knows that where 4 should map to. What it's going to learn is simply to decode out the categorical distribution where groups has a high probability. And now looking at this illustration, you notice that then this neural net is going to tell us that the following 3 groups should have as high chance as teams because 3 and 4 were mapped to a similar point. And then from that similar point, in this continuous space, you should be able to decode out a categorical distribution that's going to have high probabilities assigned to both teams and groups. So suddenly, because of this tendency of compression by this neural net training, this neural engram language model is going to tell us that the probability of groups following 3 is something non-zero, and then it's actually quite likely because 3, we saw 4 groups following 4 before, and then we knew, or this neural net knows that the 3 and 4 are similar with each other. So it automatically solves a problem of this data sparsity by automatically capturing these similarities among all these discrete tokens based on the data. So in practice, you collect a lot of data and then you train this language model. And then now my guess is that after this summer school, all of you know how to train these neural networks better than I can. So I'm not going to go into any detail here. So one thing I want to just point out quickly is that what is the usual way to report how good your language model is? One thing that people have been relying a lot on is so-called perplexity. And the definition is written down there. And then this perplexity is lower the better. And then perplexity tells us on average, how many tokens do I need to go through in this large vocabulary before I'm going to find the correct next token. So it tells us about how much uncertainty there is about making the correct prediction, or how many errors do I need to make before getting the correct answer. So when it's close to 1, that means that there's a perfect model. It's going to predict the next token perfectly every time. When it's close to the vocabulary size, then you build a very, very horrible language model. So this is the thing that people use, but perplexity is really nothing but just computing the low probability and exponentiating. So then, of course, there is the issue with the engram language model. Even though the neural engram language model is going to introduce the idea or the capability of generalization, that still does not solve the problem of the long-term dependencies. But because now we have solved the issue with the generalization or the sparsity, we can increase this n, the size of the window, indefinitely. Now, unfortunate thing is that as we increase the size of n, we tend to have more and more parameters added in the original neural engram language model. So what we actually want is to use the idea from the earlier text classification part in order to compress the variable length sequence into a single vector and then try to predict what the next one is going to be. And then that's how we are going to combine all these ideas we got from the text classification into neural language model by removing these constraints that we're going to only look at the n or n-1 many previous words. So then you can think about using a continuous backup word, right? Unfortunately, continuous backup word doesn't really work well for a language model because it turned out that unlike text classification, where we often are really interested in a very small number of the salient words or the engram in order to tell whether the input belongs to a certain category. In the case of language model, because you are trying to predict every word in the sentence, you really need to know about the actual syntactic structure as well as the semantic structure. And there are a lot of syntactic structure in our languages, many of the languages that we can imagine, do rely heavily on the order of the words as well. So on the other hand, continuous backup words, the basic idea that is encoded in this name alone says that we are going to ignore the order of these words. So that's not that great. And then empirically, in practice as well, if you try to build such a continuous backward language model, which is very straightforward to do, you're going to notice that this model actually does not work well. It's kind of, let's say, understandable, right? So we should just avoid using continuous backward, but this is a possibility, and it's a very attractive possibility because of the amazing computational efficiency it comes up with. Now then, the next one is the recurrent language model, which we're going to talk about it a bit more in detail in order to introduce the attention and then a bit more of the theoretical side of the training this language model for a long sequences. But recurrent neural net is going to allow us to compress a sequence as it reads one token at a time. And then this compressed vector can be used as part of the softmax operation so that we can get the categorical distribution over the next word in online manner as it reads a sentence. It's quite useful in practice because it works online. And then it does have a very small memory footprint as well as a computational footprint. This kind of recurrent language model often is used for autocomplete and keyword suggestion on your phones. And then it can be useful if you want to do some kind of real-time translation because it allows you to score partial hypotheses on the fly. We'll get to this a bit more in detail soon. And then, of course, as we talked about earlier, all these ideas of how to build a neural network or neural net classifier can be combined very naturally because as long as you combine them to form a directed acyclic graph, all the methodologies or the algorithms that we use to train these neural nets apply as if you build the exact, the conventional ones. That's the power of this idea of abstraction. So one idea from long time ago, 2016, is to build a recurrent memory network. Maybe we can then combine the idea of the recurrent network and self-attention in order to get the best of the both worlds. So we're going to use the recurrent neural net first in order to get all these representations. And then whenever we're trying to predict the next word, we're going to use the self-attention in order to attend to all the previous ones, regardless of how far they are. So that could actually help with the capturing the long-term dependencies. And then given that, we're going to predict the next one. And it turned out that this one has the two benefits. One is that it does work pretty well. And then the second benefit is that it does give us a slightly better idea of what were the important words in the past for predicting the next word at each time step, which is not really possible in the case of the recurrent network alone. So we've covered so far the autoregressive language model, and then how we have seen this autoregressive language model as a sequence, excuse me, of text classification. And we talked about some of the traditional approaches to language model. That was the count-based engram language model, and then we came all the way back to what our current practice is. That is a neural language model with the infinite context. So before we move on, is there any questions?
There is one. So it says, the robustness of engram model is dependent on how exhaustive are the tokens for specified language. So this is a person who's not an NLP guy, and hopefully the question makes sense.
Okay, so I mean, like, it's unclear what it means for the how exhaustive tokens are for a specific language. But okay, so one thing I can say is that it is indeed the case that when we look at the distribution of words in any language, and then even after some kind of automatic segmentation, and then looking at the distribution of those tokens, they do tend to follow they do tend to have a very heavy tail. That is that a lot of common ones appear quite a lot, but then there will be a lot of words that just appear once or twice or a very small number of times. So it has those distributions tend to have a heavy tail. Now, is that an issue? I mean, it is indeed a case that it's difficult for this neural net to learn what those rare words or what those rare words should mean because they just appear once or twice. It's impossible for even humans to do that effectively. However, what we observe is that because by building this kind of neural language model with unlimited context, there are much more signal this neural net can use than just looking at a single token. So even if that token appeared very rarely, by looking at what other context, what is the context in which this token appeared, and then in what other words appeared in this context, this neural net can actually easily tell the meaning of this very rare token as well. And then that is the power of this continuous representation and capturing the similarities automatically. So yes, definitely rarer tokens are difficult to learn from the perspective of these neural networks, just like anything, because there's just not enough statistics. However, being able to capture larger context and being able to capture the similarities among these discrete tokens that are automatically allow these neural nets to be a very powerful tool, and then can capture those tiniest learning signal there is. Okay, let me see. Oh, there is actually the chat window, and then there is a question. Okay, so George is asking, are commas typically considered as tokens as they can be semantically quite important? The answer is yes. So we tend to use everything. So many years ago, when people were interested more on those topping models and trying to cluster text according to some semantics, people used to keep the list of so-called stop words. So words that shouldn't have any semantic consequences. However, it turned out that those stop words are quite arbitrary. It's very subjective as well. And then the choice of the stop words actually does influence the final outcome as well. So in particular for the language model and any kind of generation, we do consider every token out there. Of course, we tend to remove those tokens that appear less than 5 times in the entire corpus and then map it into so-called unknown or the out of vocabulary token. But otherwise, we don't really do any kind of special process. All right, sounds good. So that was about the language model. And then I'll just have to switch my slides. Let's hope that I can do it quickly. Okay, going back. All right, there you go. All right. So there is a question from Victoria. So this is a question that I can answer actually after a bit of a generation part. So I haven't really talked about the generation yet, right? So okay, just just 1 second. Excuse me, there's a phone call. Somebody's knocking on my door. I'll be back quickly. Yeah. Well, Rodrigo, thank you. I mean, I bought something from Amazon and then apparently it has arrived. I just told them to keep it downstairs. I'll pick it up later on then. Sorry about that. But anyway, okay. So let's go continue. Before I continue, I'd like to just point a couple of the papers that I thought are quite interesting to read if you want to delve much deeper into natural language processing, because it's impossible for me to cover all those interesting ideas and the concepts within, let's say, 2-3 hours that I have today, right? One is a very recent textbook from Jacob Eisenstein titled Introduction to Natural Language Processing. And then you can actually download the draft PDF at the link that I showed you here. And also you can buy it from Amazon or whatever the bookstore you choose to use. And then the second one is more for the practitioner. Unfortunately, this book was written using a PyTorch that is slightly old, so it's not the latest version. But still, if you look at this book and then just go through it, then you'll see like a lot of the concepts that I explained here, how they could be implemented using PyTorch in order to be used with the GPU and everything. So that's going to be nice. This was authored by Dilip Rao and Brian McMahon. And then the third one, if you want to go a bit further into the neural net side of the natural language processing, and then what are the underlying mathematical ideas, then I'd like to suggest you to take a look at this. It's pretty thin. It says 311 pages, but the book itself is pretty small. Authored by Yoav Goldberg, titled Neural Network Methods for Natural Language Processing. It's pretty nice. And then this one, the preliminary version or the earlier version, can be found online for free. And then it's titled A Primer on Neural Net Models for Natural Language Processing. It was published in the Journal of Artificial Intelligence Research. So take a look at them, and then if my lecture was any unclear, then you'll find the answers there. So let's go to machine translation, because that's one of the most exciting applications in the natural language generation. And then this is one place where we have learned that having a neural network really does make some difference. So, and then the interesting thing is that already we have talked about how to build a machine translation system, and then all you need to do is build a directed acyclic graph, right? So we'll just go through how we do that one step at a time, but not too much detail, because really you have already learned it, and then you can take a look at the books that I just recommended, and you can simply code it up on the Jupyter notebook without any issue already. So what is the machine translation? We need to talk about the problem first. In machine translation, the input is a sentence written in a source language, and then output, of course, is a corresponding sentence in a target language. And as we talked about at the beginning, it is a supervised learning, and then we want our machine to be able to tell us the distribution over all possible translations, instead of just giving us a one answer. And in particular, this paradigm just fits machine translation perfectly. Because machine translation is where we have often the correct translation, but the correct translation may come in a small number of variants. So some might change the order of the words, some might change the tone of the words. They are all valid and correct, and then they can be considered as like the one translation meaning-wise, but they might come in a slight different with the different flavors, and then we want our system to capture that, but as a distribution. And then we have learned every necessary ingredient for building a full neural machine translation system, in fact. So token representation. So we're going to skip the part about how to represent the text itself into a sequence of integers, because we all know that. So how we are going to represent the token is going to be as a one-hot vector as usual. You can use space CIO, NLTK, or Moses tokenizer, or using BP or sentence piece to segment however you want. But once all those steps are done, we're going to get a sequence of one-hot vectors, which is identical to a sequence of integers. And then now, because it's a translation, unlike language model, we have two components in this directed acyclic graph. One is the encoding part. So this part is going to encode the source sentence. And then the other part is the decoding part that's going to take as the input this encoded representation of the source sentence, and then turn it into a distribution over the translation. Let's look at the encoder. And then encoder, what should the encoder do? Encoder turns the source sentence into some kind of representation or a sequence of vectors. And then that's precisely first half of the text classifier. In the text classification, what we did was to take as the input a sentence, turn it into a set of vectors, and then either max or average pull them into a fixed dimensional vector before we fed it into the usual classification pipeline. Now here, of course, we don't need to do that kind of pooling. However, we need to turn the input sentence into a setup or the sequence of vectors. So we can use, of course, recurrent nets, we can use convolutional nets, we can use self-attention, all the things that we talked about, we can use them to build this encoding part of the neural machine translation system. And then the reason why we don't want to compress them or to pull them into a single fixed dimensional vector, which was like one of the biggest mistake I've ever made in 2014, because it just becomes so difficult for neural net to compress a variable length sequence into a single fixed dimensional vector and then try to decode a variable length sequence out of this fixed dimensional vector. Because we're working on a real values vector space, of course, there we can cram in whatever we want. But in terms of learnability and efficiency, it's just not a good idea. As you see here, when we compress the thing into a single vector, these neural nets lose the capability of generalize to a longer sequences or a larger input in general. So, okay, that was the encoder. We know how to do that. That's just a text classifier cut in half. Now, what is the decoder? Decoder. What the job of decoder is to compute the distribution over all possible translations given the representation coming out of the encoder, right? So what that means is that it's really nothing but a language model, but you can think of it as the prefix that we use in order to predict what the next word should be is extended with the source sentence as well. As you see on the slides, before, for usual language model, we were looking only at this. That is the P of YT, that is the next word, given all the previous words in the same sentence or the same text. But now with the machine translation, we are looking also at X, that is the source sentence. But then wait, hold on. That's just concatenation. What that means is that the machine translation is really just a language model where the sentence is split into two partitions. First partition is the source sentence that we don't really care that much about, except in terms of prediction. And then the second part is a translation where we actually do care about predicting the next word. We just concatenate them, we build a language model, but the loss function is computed based only on the second part, the prediction on the second part. So it's really just a language model, and then we have learned already how to build language model, right? So it's really true that we already have learned how to build a neural machine translation system. And then the amazing thing is that this whole thing can be really written in one Jupyter notebook using PyTorch or whatnot. And then you can get a full-fledged machine translation system on your laptop as well. So let's see an idea how it does. Because language model in our paradigm of autoregressive modeling is just a sequence of classifiers, so we need to just think about one thing, that is how to predict the next word in the translation given all the previous words in the translation plus the source sentence. So we have a source sentence that's going to be encoded into the source sentence representation. And then we are going to have the prefix of the translation, that's y1 to yt minus 1. That's going to be also encoded into the target sentence representation. And then we need to have some large box that's going to be a directed acyclic graph that's going to turn these representation vectors from the source as well as the prefix of the translation and turn that into a single fixed dimensional vector that can be used by softmax to be turned into the categorical distribution over all possible next words in the target language. Now, then the question is, how do we fill this part in? So we're going to look at one particular example using the recurrent neural network and attention mechanism from 2015. It's quite a long time ago already, but that's the idea how the whole, let's say, neural machine translation started. So we're going to look into that one quickly before the break. So the idea is to use the recurrent neural net as much as we can, and then plug in the attention to glue them together. In the source sentence encoding part, we're going to use a bidirectional recurrent neural net in order to get the representation of each token given all the other tokens in the sentence. And then how we do so is to have the forward recurrent language model that's going to recurrent neural net that's going to encode all the previous words. And then we're going to have a reverse recurrent neural network that's going to summarize all the following words. And then we concatenate the hidden states from the recurrent neural net to get the representation of that vector. Now, we also use recurrent neural net to summarize or represent the target prefix representation, in which case we use a unidirectional recurrent network. Because we're generating one at a time, we just use the recurrent neural net on one direction, following the order of the generation. And then what it does is that it's going to essentially compress what the target prefix is, and then we are going to use the final hidden representation from this recurrent neural network. So it summarizes what has been translated so far. And we now use the attention mechanism in order to tell among all these source sentence, among the tokens in the source sentence, which one of the tokens are relevant for predicting the next target word. So given what has been translated so far, is one of the source token relevant or not? If that's relevant, then we're going to use that information in this weighted sum in order to get this so-called time-dependent context representation. Once we have the time-dependent context representation, all we need is to have a small directed acyclic graph that's going to turn this into a fixed dimensional vector, which can then be used by softmax to produce the categorical distribution over the next target word. So this is the summary of what this neural net looks like. And then again, let me emphasize that all the things that we have learned are the only things that you really need. We have learned how to represent sentence that is of variable length. We have learned how to represent sentence of prefix, or how to represent the sentence prefix. And then we have learned how to combine them using attention mechanism. And then we know that we can always plug in any arbitrary directed acyclic graph and then use the softmax at the end in order to produce a categorical distribution. So it's really just knowing about all these fundamental building blocks and then how to put them together in order to build a one end-to-end trainable machine translation system. And it turned out that such a system really does avoid the issue of the catastrophic failure when the length of the inputs change dramatically from the training set distribution. And then that was kind of the reason why we started to have some faith back then in this fully neural machine translation systems. So here are some examples. If you speak French, you'll be able to tell that the RNN search, which is this attention-based model, is doing so much better than the original one where we did not use the attention, but just a fixed dimensional vector to represent the source sentence. I don't speak French, so I can't really tell you how good it is in any detail. And then with the attention, we can actually do some kind of visualization, although there are some issues with the visualization that I want to talk about in the third part of my lecture. So, but in practice, now back then in 2015, 16, we had to code everything from scratch, but nowadays that's not anymore the case. And then if anybody wants to build a almost production grade machine translation system now, then my suggestion is to look at one of these three libraries: Marian NMT, FairSeq, and Tensor, and then try to use one of them to train a large scale model without having to worry too much about the details, and then even deploy it in production if you want. So that actually concludes the second part of my lecture. In the third part, after the break, I'm going to go deeper into attention mechanism, because attention mechanism has become one of the workhorses of deep learning, not only for language, but also for anything that you can imagine, going from the images all the way to the reinforcement learning. So we're going to go into the detail. And then after that, I'll have to decide whether I'm going to talk a bit about more recent research of mine or talk about the decoding process, because we haven't really talked about how to generate from this model other than just training this model. And before the break, let me answer the Victoria's question. What is the right way to prevent overfitting in LSTM for text generation? Very good question. One way that people have found very useful is to use the label smoothing. So instead of trying to increase the log probability of the correct token indefinitely, but we're going to only increase it up to a certain level. And then if it becomes if the probability becomes too high, we're going to actually decrease it. So that seems to be a very good way to go. And in the case of LSTM, it's unclear whether dropout is that effective. It depends, but often it's better to go for a larger data and then doing the pre-training than using a different types of the regularization algorithm. So label smoothing, I think that's a good idea. Yes. And then Marzier has a question. What is your idea about the accuracy of using machine translation models in a cross-lingual classification task or a zero-shot classification approach? This is Really interesting question. I guess I have to be careful because I don't want to contradict what Katharina may have answered already. So strictly saying, I think the ideal scenario is to be able to build a multilingual system and then do zero-shot classification. And then what we hope is that because the transfer of knowledge from one language to another is going to happen in the continuous vector space, that is going to have a more flexibility and better generalization. However, in practice, we often see that it's very strong baseline to use a strong machine translation system to translate either training or the test set, or often the training set, and train a target language classification model. I think that one of the reasons is that we still don't know well what is the right way to regularize the structure in this continuous space, because this continuous space is gigantic and there can be a lot of holes in it. On the other hand, when we work at the actual input level, and then with the machine translation, we know that there are some limited number of the translation mistakes or the translated text that we're going to get, and then that seems to make sure that this classifier is not going to make a weird and stupid mistake. So if you have to build any cross-lingual system now, classification system now, I would suggest you to start with a machine translation of the training examples. But then in the future, hopefully when the research is done further and then we become much better at understanding and imposing the constraint on the structure of the continuous space, we probably could go into the zero-shot classification. Okay, one last question before we go into the break, because I want you to all get some break as well, right? So George asked, are there any best practice to adapt a pre-trained model to domain-specific language, chemistry with reaction equations? Oh, I mean, I don't think there is no a best practice, but especially if you know the domain, then you can start with the pre-trained model that was trained on a generic domain like the Wikipedia and so on, and then trying to collect more data that doesn't have to be annotated to fine-tune this model a bit toward the target domain, and then use it for the actual target problem seems to be a good idea. There are a few such cases like that. For instance, when you look at not one example is like the BioBERT or the SciBERT, which is a BERT that is fine-tuned on the target domain unlabeled data. And then they tend to work better for the problems in the target domain just because they have less mismatch in terms of vocabulary overlap, or the less mismatch in terms of the kind of, let's say, the way in which the sentences are formed. So yeah, definitely think about this kind of two-stage pre-training. But again, this is not a solved problem. A lot of people are working on it, and often the best practice is specialized for each of the target problem they are solving. All right, so we're going to take, although we only have 2 minutes, but let's say we take a break for 7 minutes. What do you think, Rodrigo?
Let's do it. Yeah. So now we have taken a bit longer, and then also you have these interruptions. So it's no problem if we continue at, let's say, so 7:05, so 7 minutes from now.
Okay, let's do this. 7:05. Sounds good. I'll see you all back then. Yes.
See you in a bit.
Okay. I hope people are already back. I mean, like it's quite exhausting just sitting here, right, for 3 hours, 2 hours, and then now the third hour begins. So this hour, I'm going to spend some time talking about attention mechanism once more, because this really has become one of the most key components in building these modern neural networks. And then if time permits, I'll try to talk a bit about the decoding algorithm and then some consequences from there on. Oops, I'm sorry. I don't know what just happened, but let me just reconnect my iPad. Let me just restart my share. Sorry about that. Screen just suddenly disappeared. What happened? Let me just retry. Oh, there you go. Whew. I know this kind of thing always happens somehow, right? Okay. All right. So yeah, attention mechanism. Let's delve deeper into this. So if you remember from what we just talked about, that is that this attention mechanism already in 2015 when we designed it, especially the Dima Badanao, the first author of this paper, designed it. It was a idea that was very much focused on the fact that we have to deal with the input that has a variable length. So before this idea, often it was never a trivial to build a neural net that is able to deal with the input whose size changes dramatically. The best way we knew how to do and then what was used was to use the convolution together with some kind of pooling at the very end, global pooling, or just using a recurrent neural net and then asking the recurrent neural net to somehow compress the entire thing into a single vector. Now, both of them do work to a certain degree, but in machine translation, where it was really important for our neural network not to lose any information about the input, because in order to translate a source sentence, you really need to keep all the information about the source sentence. Both of those approaches that tend to work as compressing the entire input into a single vector did not work well. So the attention had to be made. But then once you make this kind of thing and then you see that, oh, this one works really well, then you start wonder often the other way around by saying that, well, what is the right way to derive, or what are the different ways to derive the attention? And then thus that kind of derivation actually allows us to have a different type of intuition. So now let's look at another way to derive that attention, because here we have derived the attention in a way that just intuitively makes sense, but that's not really based on anything else. It was just out of thin air. Can we actually arrive at attention from another angle? To do so, we need to actually talk about the recurrent language model a bit further. And then one way to view recurrent language model is building a neural network that's going to have a recurrent connection. And then this one is going to be applied over and over. And then when it's unrolled, it looks as if we have a deep neural network with as many hidden layers there are the tokens in the source sentence or the sentence itself. And then the whole process can be described by iteratively performing read, update, and predict. So we're going to read the next word, update the hidden state, and then based on that, we're going to predict the next word, one after. And then in doing so, we can now divide this whole recurrent network into two parts. One is a transition function, that is taking into account what the current word is, and then trying to update its own hidden state. So it takes as the input previous or current. Is kind of, let's say, confusing because is the next one current or something like that, but it takes as input what we see now, that is the xt minus 1, and then it looks at what the previous state was. So what is my memory state? That is ht minus 1. And it has parameters like the input weight matrix, transition matrix, and bias. And then often we study this naive transition function, where this naivety comes from the fact that we simply concatenate this xt minus 1 and ht minus 1, apply the linear transformation by multiplying it with a matrix that is a concatenation of w and u. After adding some bias, we apply the element-wise nonlinear function. So let's say we're going to use this naive transition function for now. And what this does is that it reads the current word and it reads the previous hidden state and then updates the whole memory on its own. So this is the read and update part. Once our memory is updated, that is, we have the HT now, we should be able to predict what the next word is going to be. And then the prediction, as I'm talking about it over and over, you must be getting tired of it, is done by having a neural net output a categorical distribution. And this categorical distributions is defined over all possible next words. And we use softmax. So we're going to apply the I'm sorry. So apply the affine transformation and then apply softmax in order to get the distribution over all possible next words. So this is the part that is read. So we had the, well, that's not the read. I'm sorry. So we had the read and then update part already with the transition function. Now with the readout function, we do now the prediction. Okay, so that's good. And then training, we know how to train it because it's just a language model. So we're going to train it as a text classifier where every word in the sentence works as the target. And then we define the look likelihood functional as shown here, and simply to minimize the negation of this. It's the same as maximizing the original look likelihood, but somehow, the optimization people always love to minimize rather than maximize, right? Now, so what we talked about is that once we have this directed acyclic graph, although recurrent neural network by definition is not acyclic, it's like almost by definition cyclic. However, what we're going to do is that given any input sentence or given any sentence, we're going to unroll this recurrent neural net. And then we end up again with a directed acyclic graph. And once we have the directed acyclic graph, we said that, we can leave the computation of the gradient of the loss function with respect to all the parameters in this network to the automatic differentiation. However, it turned out that it sometimes helps to look at what actually happens. And in particular, with the naive transition function, it turned out that it's very important to see what is done in order to compute this gradient. And then that tells us a lot about what we should do in order to build this directed acyclic graph. So let's just look at this algorithm called backpropagation through time. It's really nothing that has anything to do with the time, but there's the original term. And then we're going to look at each time step, because what happens is we're going to have the replicate of this computation over time. And then at each time step, we're going to predict the next word. So we actually get the loss at each time step separately. And then we can now think about applying the backpropagation at each time step. And then what happens is that we are going to compute the cost derivative. So we're going to look at the per step, so the loss function at that point. And then we need to compute the gradient or the gradient with respect to G. That is a readout function. We talked about readout function now. And then we want to compute the gradient of this per step loss function with respect to R. R was the parameter of the affine transformation in the readout function. And then how you do that is by multiplying the gradient or the partial derivative of the log P of predicting the next one with respect to G, the output of the readout function, with the Jacobian of the output of the readout function with respect to this R, the parameters. And then that's essentially where the chain rule is being used, right? And then we now compute the gradient with respect to this state HT. Now, this is the very interesting part. So we're going to multiply this partial derivative of the loss at time step t with respect to the output of the readout. And then now we need to multiply that with the Jacobian of G, the output of the readout with respect to the input to this readout, that's HT. That's fine, so far so good. But then you notice that we actually had an outgoing edge that not only goes into the readout, but also to the next time step. So what that means is that the gradient of the entire loss function, that is a sum of the per step loss function with respect to this HT hidden state, should be the sum of what we just talked about plus the gradient that have been propagated back through time via this temporal connection we have. And then we just write it further and further, and then we notice that the gradient of the gradient of the whole, let's say, loss function, the total loss function with respect to W as well as B, all depend on both the gradient coming from the current time step as well as the gradient coming from the future time steps. And then it's going to be accumulated over and over. So intuitively, what does that mean? Is that in order to compute the gradient of the parameters in this kind of recurrent neural network, we need to think not only about what happens when I change my parameter in time step t, but I need to think about if I change this parameter, what happens in the future. And then we need, in order to compute what happens in the future, I just need to accumulate what happens at every different time difference. I'm going to just accumulate them. And then I now know that what's going to happen there. So that's an interesting idea. But then you realize that this is not the best thing that could happen, because this accumulation is expressed not as the summation, but as the product. So we need to look at what happens at every time difference, and then we multiply all those effects. Then that's the effect that I have on all the future time steps. And then that's not that good. Why is that not good? Because once we multiply some constant or this something over and over, you start getting a weird effect. Let's just imagine this simple scenario. Let's say it was just a one scalar. It's a real value scalar that's slightly larger than 1. So it's going to be like 1.1. What happens if I multiply this over and over? It's going to rapidly, exponentially diverge toward infinity. Now, on the other hand, if I had a scalar that's slightly smaller than 1, let's say 0.99, if I multiply it over and over, it's going to rapidly converge to 0. And then in backpropagation through time, the exactly same thing happens, because we end up multiplying this entry that is a U, that is a transition matrix transpose times the diagonal matrix built out of the partial derivative or the Jacobian of the output of the hidden state. So the output of the update part with respect to the input to that one. And then when we look at because we are now looking at the matrix, if the largest eigenvalue or the eigenvalue of this U, the transition matrix, is larger than 1, it's very likely that this whole thing is going to blow up, just like when we multiplied, let's say 1.01 a lot and a lot. On the other hand, if this maximum eigenvalue, largest eigenvalue, is smaller than 1, then the norm of this whole thing is going to rapidly vanish towards 0. Just like when we multiply the 0.99 over and over. And then these two turned out to be extremely important problem that kind of, let's say, discouraged the entire community to start working on recurrent neural net for many, actually a couple of decades. And we call it vanishing and exploding gradients. Fortunately, the exploding gradient turned out to be very, relatively easy to handle. Whenever this explosion happens, that is that the norm of the gradient is really, really large, we're simply going to say that, okay, we do not trust the norm of the gradient. And then this is actually very interesting thing about the gradient descent, and in particular stochastic gradient descent, is that the gradient tells us about the direction toward which we can move in order to increase or decrease, depending on whether you follow the positive or the negative direction. Let's say positive direction, increase the function, or the function of which you compute the gradient. Now, but it's only valid locally, right? Unless you have a very nicely behaving function, this is valid only locally. And then there's a question of how much can I trust the magnitude? Or does magnitude even matter in this particular case? So what that means is that we can trust the direction, that if I follow the direction, or the negation of that is going to either increase or decrease the function value. However, it's unclear whether I should follow the direction according to the magnitude of the gradient. And then in fact, what this exploding gradient tells us is that if you follow the gradient direction, gradient magnitude as well, then we're going to completely throw ourselves away, throw ourselves off the path. So what the exploding gradient tells us is that we shouldn't just really trust the norm of the gradient, and then we should simply stick to the direction of the gradient. And then whenever the norm is large, we're going to simply say that, yep, we're not going to follow the norm magnitude. We're going to just follow the direction with the max step that we're going to decide. So, and then that's called gradient clipping. There are different ways to do so. Turned out to be very, very effective. The issue is with the vanishing gradient. We actually cannot tell why vanishing gradient happens. Well, to be specific, we cannot tell which of the reasons for vanishing gradient actually happen. So there are two ways that vanishing gradient can happen. One is that there is just no long-term dependency to capture between time step t and t+1 n in data, right? That is, the training is over. So we trained everything, and then the norm of the gradient should vanish to 0. That's the whole idea about the gradient descent, right? The other possibility is that the configuration of the parameters is just not good. That is that we configure the parameters or even initialize the transition matrix to have a too small a largest eigenvalue. So even if there is something to capture in the data, the norm of the gradient just vanishes too quickly to 0, and then learning just cannot happen efficiently. But we don't know which one is actually the true case. That makes it really, really difficult. There have been some ways to avoid this, but none of them has been that successful just because there's no way we can actually distinguish between these two potential causes. So that's where we need to start thinking about the completely different way to do so. And by considering that the whole issue comes from the fact that the backpropagation is happening through all the intermediate layers. So let's just look at the temporal difference between these t and t plus n. What happens is the temporal difference is going to the multiplication, or can be written down as the product of the temporal differences of every layer. And then perhaps that's an issue. What if we say that we're going to create all these shortcut connections that bypasses all these time steps? Would that actually avoid the issue? It looks like so, because without the shortcut connection, we have the temporal difference between time step t and t+1 has to be written down as the product of all these intermediate changes. However, if I had a shortcut connection, then this temporal difference is going to be described as a sum of the temporal differences of all these shortcut connections. So then there will be shortcut connection that's not going to have any of those repeated product. And then for that part is going to allow us to capture those long-term dependencies without having to be bogged down by the product of the same term over and over. Now, of course, just introducing all those shortcut connections is kind of difficult. People already tried it in only 9s and so on. The difficulty comes from the fact that every connection we add in these neural nets often implies that we need to add extra set of parameters. And then number of shortcut connections that we introduce directly impact the number of the terms in this product when we compute the temporal dependency. So we want to introduce as many shortcut connections as possible. However, that increases the number of parameters greatly. So we don't want that. So instead, we can think of a way to introduce a shortcut connections adaptively. That is, we're not going to add all possible shortcut connections, but we're going to add only a few shortcut connections only when it's deemed necessary. And how we do it is to introduce the idea of the gating. So at each time step, we're going to either take the new hidden state value, or we're going to use the previous hidden state value as it is. Now, of course, this is not going to happen at the entire vector level, but at each dimension. So for some dimensions, we're not going to update it. We're going to simply carry over the previous step's value as it is. And then that one works as if a new shortcut connection was introduced. For some other dimensions, we're going to replace it with a new value. And then that one works as if the shortcut connection was not introduced. And then, of course, the hard decision, that is making the decision of either 0 or 1, is very difficult in neural network because that function is not differentiable. So we are going to use a more relaxed definition of introducing a shortcut or not. That is, we're going to introduce a shortcut with some degree that is continuous between 0 and 1. So that's why we use the sigmoid function here. And then that decision is going to be made based on the actual input. So this is how we're going to introduce adaptive shortcut connection. But then one thing about this connection is that as we introduce more and more connections, it becomes increasingly more difficult to do the credit assignment. And then backpropagation procedure, that is the application of the chain rule of derivative, is a procedure of what changes in the intermediate layers led to changes in the outcome. So that is assigning the credit or blame, if you want to use a more negative term, right? And then if there are many connections, then the signal is diffused further. So you want to ensure that the computation going forward has many shortcut connections, but that shouldn't really increase the number of total connections too much. So what we're going to do is we're going to also adaptively prune some of the shortcuts. And then that is going to be done by the reset gate. Now you get the idea, right? So we use the update gate in order to introduce the shortcut connection adaptively. And then we use reset gate to prune adaptively some of the shortcut connections. So it's an idea that is quite familiar if you're a computer science, let's say, if you have a computer science background, because if you think about this recurrent neural net as implementing a CPU in our laptops and computers, then you notice that this recurrent neural net with a naive transition that we looked at that uses the hyperbolic tangents unit is a bit unrealistic. So what does it do? It's going to read the entire register, the values in this memory, and then it's going to do some computation and then update the entire register. That's not how it often works. In CPU, how we are going to do is that we're going to choose a specific instruction, and then that instruction is going to access a specific part of the register, and then do some computation, and then update only a specific part of register. But in this hyperbolic tangent, as I say, this naive transition recurrent neural net, that's not the case. On the other hand, if you look at this gated recurrent unit or LSTM in general, this one has a much, let's say, this operates in a much more similar way to CPU. It's going to first select, a readable subset R based on the reset gate, and then it does the computation based only on that subset that has been read, and then the result is going to be written to this writable subset that was selected by the update gate. And then all the other values stays as they are. What that means is that this is so much more realistic implementation of how the recurrent computation should be done if you view it, or if you make an analogy to how the computers work in general. So the key idea behind LSTM and GRU is this additive update. Instead of replacing all the values every time, we're going to add some value to the existing memory and then subtract some values from the existing memory. So make everything additive. And then that's how we are going to make a connection to attention mechanism. So it's not really a side note. I don't know why I put side note there. Now let's try to rewrite this gated recurrent unit by unrolling the whole computation. So if I wanted to compute the HT, it's going to be a convex sum between HT minus 1 and tilde HT, that is a new value. Now I can rewrite HT minus 1 as a convex sum between HT minus 2 and the new value of HT minus 1 tilde. Now I can rewrite the HT minus 2 as a convex sum of the HT minus 3 and then the HT minus 2 tilde. And then I can do that for HT minus 3 as well, and then go on. And then eventually what we end up with is a weighted combination of all previous hidden vectors. So it's a weighted. Weighting is going to be done by some combination of these weight gates, update gates, and then it's going to be the sum of all the hidden vectors weighted by these weights. And then from there, you start thinking, do we actually have to make these weights dependent on each other? Maybe we can simply free them to be whatever they are. Because at the moment, these weights are computed as a product of the many update gates. And then those update gates are all dependent on each other. So can we just remove the dependence? That's the first step toward getting to the attention mechanism. And then now let's use the alpha I instead of this complicated product that we use to weight each of the vector. And then this alpha can be computed as the relational module or the relationless output between ht tilde and then xt, the input there. And then and we do some kind of normalization because the original weight sum to 1. So we're going to make them sum to 1 by using softmax. And then the second step is that you realize that the hi tilde again depends on all the h tildes from the previous time step. So these values are not independent from each other. They are all codependent on each other, and then they need to be computed sequentially. But perhaps we don't need to do that. What if we simply say that this hi tilde is computed solely based on xi, that is input at ith position, with some neuron at x? Okay, so we got a bit even closer to this self-attention. Now the third step is to say that do we actually need to use the same value to compute the weights as well as compute the ht, the hidden state? Perhaps that's not the case. Perhaps what we can do is we can get 3 different types of the vectors from the input, that is the key, query, and value. And we use the query and value to see whether those pair of the vectors are relevant to each other for this time step. And then we use value to get the value that is going to be weighted summed and then passed to the next layer. And then at this point, if you are familiar with it, you're going to notice that this is precisely what the attention mechanism is. Already from the differentiable memory network or the end-to-end memory network in 2016 to transformers in 2017, this is precisely the key value attention mechanism people have been using. And then the final step there is to realize that the key value and attention query, it doesn't have to be a single triple of them. There could be multiple of them. So we could have the multiple attention heads. And then the output from this attention is going to be the concatenation of the results from the k-many attention mechanism. So what this tells us is that one of the reasons why attention is powerful is because this attention creates all these shortcut connections, and then these shortcut connections are all additive. Just like how we ended up having a gated recurrent units for LSTM in order to avoid the issue of the vanishing gradient by introducing shortcut connections, what this attention mechanism does is also to introduce all these shortcut connections additively. And then to be more efficient computationally, it broke down all those temporal dependencies. And furthermore, with this in your mind, unlike recurrent network, which has to go in one direction, now we can actually compute everything all together, looking at the future as well. Because if you have noticed, this whole thing does not depend on the order of the input. So the order was encoded in having these weights being dependent on each other, candidate vectors being dependent on each other, but we freed these two, or we relaxed these two constraints. So this attention works without regard to the order. What that means is that we can just apply it to the entire input rather than only to the previous vectors, which was the case up until now. And then that's how you end up with a non-causal attention. Now, one thing I want to talk about is that the attention does not depend on the order of the input vectors. And that's not good because we know that the order matters. So what people have been doing is to use so-called positional embedding. Why is that so? It's because when you vary the order of the vectors, attention won't make any changes. However, by adding some position specific vectors, 1, 2, 3, 4, then now suddenly the attention is going to know the order and then become aware of the order and then knows how to use that information for computing the hidden state next time. And then there are many different ways to do so. You can either learn this positional embedding directly, or you can use a sinusoidal positional embedding that allows you to apply this attention mechanism to the sequence that's going to be longer than the one that was used during training. And lastly, I don't know if you have noticed, the original attention that I just showed you, the one that we have derived so far, is very linear because it's just a weighted sum of the input vectors. So what you want is that you want to apply some kind of non-linearity after using this attention. And this G is often a fit for neural network, as in the transformer blocks. And then this is the full self-attention layer that we can derive starting from a naive transition recurrent neural net, going to the GRU and LSTM, and coming here by removing a lot of sequential dependencies. And once you stack all of them on top of each other, you can build the recurrent the neural machine translation system, just like I have demonstrated earlier with our system from 2015. And then nowadays we call them transformers. And then that is the model from the Vassanio 2017, titled "Attention is all you need." And then it does consist of the multi-headed attention, residual connection, fit for layer, point-wise nonlinearity, and another residual connection, followed by normalization. So it really does use all the things that you have learned so far, and then I have taught you today. And then you end up with a state-of-the-art machine translation system that relies almost entirely on attention mechanism. So we have talked about the language model, machine translation, and attention mechanism. And unfortunately, we are running out of time, but is there any questions up to this point before we talk about the decoding briefly before we finalize the lecture? Rodrigo, is there any questions somewhere?
No, they aren't at the moment. So
okay, no questions. So then just give me a second. Let me just switch my slide. Let me see. Okay. Let's see. All right. So we don't have much time, so I'll have to go quickly. One thing I'm actually sad that there was no question because I never actually mentioned about how to generate a translation out of this system. So we know how to train it, we know how to build it, but what is the right way to do actually generate a translation given a new sentence after training is done? So in order to go into that, which is the problem of inference or the search in this particular case, let me just give you one kind of example application of this whole procedure of building a machine translation system, and that is the neural dialogue modeling. It turned out that this kind of neural machine translation system we built in 2014 and 15 are extremely generic. Because if you remember, in my description of these methods, there was absolutely no mention of whether the problem has to be actual translation. Only thing that we talked about was that the input is going to be some sequence of discrete tokens, and then output is also going to be some sequence of discrete tokens. And then what that means is that as long as we have those sequences, and even on the input side, it doesn't even have sequence because as long as it's a sequence of the set of the continuous variables, then we can actually use it for whatever the purpose you want. And then one such example is this is a typo, is a neural conversation model. That is, instead of looking at it, trying to solve the translation, we're going to solve a translation that we're going to build a translation system for modeling a conversation. And then what does it mean to model the conversation? We want to train this model to read what has been said and then trying to predict what's going to happen or what should be said based on the profile. And it turned out that it doesn't really require too much of the magic or techniques. All we need to do is simply flatten the sequence of personality description and previous utterances, all of them, and then say that, okay, this is my source sentence. And then what we do is we're going to say that the target is going to be, again, a flattened sequence of human or annotator's response. suddenly we have a translation problem. But this is not really language A to language B translation, but it's more like the previous utterances to the next utterance translation problem. And then everything that we have talked about applies identically without any change to this neural conversation model. We build a autoregressive language model that is conditioned on the source as usual. And then we train it to maximize the log probability of the correct response or minimize the negative log probability of the correct response. And then we know really how to do it really well. We learned everything. We talked about the recurrent nets. We talked about the convolutional nets. We talked about the transformers. And then we know that as long as we put everything into directed acyclic graph, backpropagation can be done automatically. And then optimization algorithms are already implemented, so we can just train it. Then we know how to use it. But then one thing that we haven't talked about is how to use it. So we know how to build it, but using it is slightly different from building it. Once we build this system, what we get is the distribution over all possible translations or the responses given the previous utterances. And then there are exponentially many possible responses given that the length, even if the max length is fixed. So it's a pretty large space. So we cannot really try the exhaustive search. We cannot try every possible response and then choose the one that has the high score according to this model. Furthermore, it's not even clear whether that's what we want to do. But however, unfortunately, that's out of the scope of this lecture. So we have to rely on some kind of approximate and sequential local search. So we have to come up with an algorithm that's going to take only linear or the polynomial term with respect to the length of the response that we're going to decode out. And then linear is, of course, always preferred. Even polynomial time is difficult in practice. And then there are two major approaches that have been used. One is greedy search, and then the other is a beam search. And greedy search is very simple and then does exploit the fact that we are doing autoregressive modeling. Because we're doing the autoregressive modeling, we have the probability distribution of next word at every time step. And then we're simply going in greedy search simply picks the best one accordingly. Now, unfortunately, that's not the best way to go. Why is that? Because our choice does not take into account the future consequence. So my choice that looks nice at time step t may be a horrible choice when we look later and then look at the entire sequence. So it has been found that it's quite suboptimal and it's very undesirable to use a greedy search. So then we can actually be a bit better by thinking about beam search. So instead of taking top 1, we're going to take top k every time. So we're going to maintain k many possibilities so that later on we can choose the one that is best, not according to the individual local criterion, but based on the global criterion. And then we can now easily control the complexity by changing the number of the hypotheses that we're going to carry over. So this is good, and then it's a very simple idea, but it is a bit involved to describe this in detail. But the most important thing is that every time we make a choice, we need to look at the global criteria. That is, we need to look at the score of the entire prefix or the entire sentence, rather than just a local score. And then at the very end, we're going to choose the one among these k many hypotheses, the one that has the high score according to your criterion. Doesn't have to be the log probability in fact. And then this connects to the earlier discussion about the all-list stopping, where the log probabilities may not be the one that correlate perfectly with our task cost. And then if we could compute the proxy to the task cost better, then we should actually use that for all-list stopping. And then that applies to beam search as well. Once we get this set of hypotheses coming out of the beam search, then the choice of which one you're going to use as a final decision or the final translation has to depend on not only on the log probability, but on the desired properties that you want to impose. So that's just important detail to think about. And then let's see what that means graphically. So we are going to keep the hypothesis at some time step, t-1. Then we're going to expand each hypothesis with the possible next words. And then among them, we're going to sort and then find a smaller set of candidates. And then that's going to be considered as a candidate for the next time step. And then we do it over and over. Eventually, we end up with a small set of a final hypothesis from which we need to choose the one answer. So here's a global view that we looked at earlier. Now, of course, these two are the most widely used inference algorithms or the search algorithms, but you can be actually much better, or if your goal is slightly different. Because all these algorithms are approximate, they are not going to look at the as diverse set of candidates in order to make a decision. So then can we actually make it or force the beam search or this kind of approximate algorithm to look at more diverse candidates? It turned out that it's possible, and it's quite easy to come up with it. There are so many different ways to go about. One idea is to run the beam search over and over, but every time we run beam search, we're going to ensure that any candidates from the previous time steps are going to be blocked out, so that it's going to explore a different part of the space more effectively. Of course, another way to do so is to introduce the stochasticity. Instead of trying to come up with a deterministic algorithm, we can try to come up with a stochastic algorithm that's going to have a chance to explore parts that gets small probability as well, as long as it's not zero. We can use the ancestral sampling, but ancestral sampling tends to find those hypotheses that are too weird, or the ones that are too small a probability. So what people often do is to is so-called top K sampling, where they're going to reduce the search space at each time step to only the top K tokens, and then removing all the others. And then from there, they do the actual stochastic sampling. It can give you a more diverse set of sequences, as well as to avoid some of the degenerate cases. However, stochastic behavior is always a bit problematic if you want to deploy it in production systems, or if you want to debug anything about it, because the behavior is inherently stochastic and it cannot be reproduced easily. So that's how you do the search. And then I'll have to skip about the human evaluation, although it's a very fascinating topic. I'll just show you whether the search algorithms actually do make difference. So we did this very simple experiment study of using a translation system for dialogue conversation modeling, and then we did a human evaluation. So we asked the mechanical Turker to have a conversation with this machine translation system or the conversation system, and then ask them to give us a score between 1, 2, 4, 3, and 4. We 1, 2, 4, and 5. We removed the 3 because we wanted to avoid any kind of, let's say, catch-all category. And then we used one model that was trained once, but with a different search algorithm. We tried greedy, beam search, as well as the iterative beam search. And then as you see here, you should look at this column in particular. It really matters which search algorithm you use. So in this particular case, iterative beam search was the best approach, while greedy search was the worst approach. And then again, this is just a one model. So what happens is that in this kind of structured prediction algorithm, where the output space is structured and combinatorial, it not only matters how we train this model, but it also matters how we use this model. And then that's also an actively researched area. And then when you build this kind of system and then use it for your purpose, you always have to be mindful that the potentially suboptimal performance that you may see may not be due only to the learning or the architecture, but also to the choice of the inference algorithm that you use. And then this is really important lesson that took me some time to realize. But anyway, so this actually concludes my 3-hour lecture. Thanks for bearing with me all along. And then now I'm actually ending it in time so that I have enough 10 minutes or even 11 minutes to answer any of the questions you may have. Rodrigo, is there any questions on the YouTube or Slido or whatnot?
Yes, so the one is if the training process accounts for typos, or how do we handle typos?
I see. So this is a really interesting question. So typos are a kind of difficult thing to actually define. So sometimes, so for obvious ones, you can actually easily tell whether a written, whatever is given is typo or not. But sometimes it's quite difficult to tell whether that's intentional or unintentional typo. So for if you know that you want to build a system that is used for the formal document or the more in a formal setup, then you want to clean up the training data offline in order to avoid having weird typo so that the model is not going to mistakenly generate any kind of typoed output. However, in many cases, it's impossible to tell whether certain things are typo or not. And then in particular, we cannot really expect that users are not going to make any typos in advance. So it may be even better for our system to be trained on the text with typos so that it's going to be more robust to those cases. So it's even a good idea to introduce typos intentionally in order to make a model robust on the input side. But on the output side, you want to clean that up depending on whether you want to do it. But if you think about the conversation modeling, and if you want to build a chatbot, sometimes people do make an intentional typo in order to make a point. And maybe those cases you do not want to remove them. So long story short, on the input side, if you could try to stochastically introduce all those typos and so on in order to build your system more robust. On the output side, you'll have to clean it as much as you can based on the target audience and the target domain. Okay.
And another question is if you can maybe say some words about emotional conversational models using neural networks.
Oh, unfortunately, I'm not really familiar with this, the emotional text processing and so on. One particular person that I know who has been working on this direction is a Pascal Fung at Hong Kong University of Science and Technology. She has done quite a bit of work on the building a emotional chatbots and then the emotional text processing. So you might want to take a look at her work, but I'm not really a big, I'm not too familiar with this topic myself.
And a follow-up question regarding typos is that, so the most common typos, shouldn't they be mapped to the closest match with some probability?
Yeah, so that's a perfect observation in a sense that we talked about how these neural nets are going to capture the similarities among all these tokens, and then most of the typos are most similar to their original words. So they are going to have a very similar word vectors and then have a very similar effect as non-typoed words as well. However, that only makes sense for the typos that are seen frequently enough. If the typos are very, very rare, it's unlikely that they're going to be close to the original word on its own. So that's why I talked about it makes sense to introduce artificial typos in your source, in your data, especially on the input side, so the model is going to learn about the typos automatically itself. Now on the target side, that's actually an issue that the model is going to put a similar probabilities to the original or the correct clean one as well as the typoed or the noisy ones, because then there's a chance that this network is going to make a mistake of outputting the noisy version rather than the clean version. That's the reason why you want to clean up as much as you can on the target side rather than the input side. Okay, I see the, yeah. Mm-hmm.
There is question, so if a system is trained on a type of free text corpus, are there any studies how robust the model is against that?
Oh, that's a good question, but I thought Zach was here to give a talk. Zach must have mentioned about it, if I remember correctly, right? So these systems are not robust to the simple typos, and then there are many reasons for that. Let's say you build a system that works at the character or the letter level. So there's no, let's say, words that are unknown to this system. And then you can think of it as if having an adversarial examples in these computer vision systems. So you can always have a system that's going to have a erratic behavior when only one letter changed, which shouldn't have mattered at all. So that happens. And the second case is that when you're working with this kind of token, like the byte pair encoded token or the sentence piece encoded token, or even the words directly, some of the words, when the typo is introduced, may become out of vocabulary words. so it doesn't exist in the vocabulary, and it's going to be mapped to those special tokens. And then suddenly the input just changes. So then the model's behavior will change as well. So that's the reason why I'm talking about this, introducing noise into the input so that the model is going to be more robust to these possible changes or the noise that it might encounter in the test.
Right. Well, it seems that's everything for today. In any case, tomorrow we'll have a longer block dedicated to question and answers. And yeah, so now we can conclude with these 3 hours of insightful an insightful introduction to NLP.
Okay, thank you very much. I mean, thanks for listening to this long the lecture, and then I hope to hear more from you actually tomorrow then.
But I must say it passed so fast. I realized, wow, so now 3 hours are gone. It was it was a safari, but a very fast one and very well paced.
Okay, happy to hear that. I'll see you all tomorrow. Good night then.
Then see you tomorrow.
Thank you for the lecture.